Okay, let's get into it. It's first assignment of the winter break to start rebuilding your score. Okay, so I'm going to assume that we did the reaction. I'm going to say that I saw the color red. I'm not going to do all of them. We're going to go through just one version. They're all kind of the same. They just have slightly different values. So if I'm assuming that I saw red, that's going to put me, according to the scale here, between 625 to 750 nanometers. So all I had to do was pick a value between 625 and 750. Okay. Now, once I have my value, right, then I have to understand that this is going to use the formula wavelength is equal to the speed of light divided by the frequency. Okay. Now, keep in mind that this is in nanometers. So if I have 650 nanometers, sorry, 650 nanometers, I have to convert that, right? And that's the conversion factor that I gave you on the board. So I know that for every 1 nanometer, there are 1 times 10 to the negative 9 meters. Okay, nanometers cancel. If nanometers cancel, I'm left with 6.50 times 10 to the negative 7 meters. I need my unit in meters because the speed of light is equal to 2.99 times 10 to the 8 meters per second. Notice that this is in meters, not in nanometers. So because it's in meters, I have to convert my nanometers to meters in order for those units to cancel. This is what I meant when I say you need to keep track of your units. You need to keep track of your units so you know what to cancel and where. Now, if I have a value of wavelength and I know that speed of light is constant, right? Because now my wavelength is equal to 6.50 times 10 to the negative 7 meters, right? Then what I'm looking for is the frequency, right? I'm looking for the frequency. So let's do the algebra. Divided by the frequency. If I multiply both sides by frequency, they're going to cancel. And then this becomes frequency times the wavelength is equal to the speed of light. Now, I need to get frequency by itself. So if I'm going to get frequency by itself, I can get rid of the wavelength by dividing by it, right? So if I want to figure out the frequency of this particular wave, right, I need to take the speed of light and divide it by the wavelength. So we already have those values. We know that the speed of light is 2.99. If you use 3, that's fine too. Times 10 to the 8 meters per second. And I'm going to divide that now by the 6.50 times 10 to the negative 7 meters, right? These are going to cancel. And I'm going to be left with 4.6 times 10 to the 14th seconds negative 1, right? This is also written as 1 over seconds, right? Or you can write it as hertz, okay? So this is equal to my frequency. Okay, so that was the solution for question number 1. Okay, let's see here. Yeah, question number 1. All right, let's move on to question number 2. Question number 2 says, how much energy is present in this wave? Calculate the energy of the wave emitted in the reaction. Okay, well, from your notes, you should have known that energy of a wave is equal to Planck's constant times the velocity or frequency of the wave, right? The frequency of the wave. Okay, now we already figured out the frequency. It's here, right? This is, in this case, it's interchangeable. So I know that energy is what I'm looking for, right? That's my unknown. I know that Planck's constant is 6.636 times 10 to the negative 34, and this is joules times seconds. Okay, and I know the value of the frequency or the velocity here. That's equal to 4.6 times 10 to the 14th, and that's 1 over seconds, or seconds minus 1, however you want to do it, okay? This is a very, very simple plug in the values and calculate the energy. So let's do that. All right. Energy is equal, and I'm going to put it down here below, Planck's constant, 6.636 times 10 to the negative 34. This is going to be joules times seconds. Then I'm going to multiply that by 4.6 times 10 to the 14th, 1 over seconds. Okay. In this case, seconds cancel. Okay. And I just multiply the values. Now, I didn't have you do this by hand. I had you do it by calculator, right? So you literally just have to plug it into the calculator and get the answer. So the energy of this wave is equal to the product of these two numbers here. And I ended up with 3.052, right? 56 times 10 to the negative 19. Seconds cancel, so we're left with just joules. Now, if you rounded this, you should have ended up somewhere at 0.53 times 10 to the negative 19 joules, and this was the answer for number 2. You take the value you calculated in the first one, and you literally just plug it into this equation right here, and you get your answer. Okay? That was full credit for number 2. Okay. Let's get to number 3. So this one was pretty simple question. You could have calculated it, but if you didn't, you shouldn't have had to calculate. Okay. Let's say that second reaction. So I'll put it here. Second reaction. Okay, let's say the color was green, right, or violet or blue, but we'll go with green, right? So I'll put green. Okay, so green, right, has higher energy. So I'm going to put green here with a G, has higher energy. Why does it have higher energy? It has higher energy because it has a higher frequency. It has a higher frequency. As a result of having a higher frequency, that means that what's happening is the wave is going from a red wave that looks like this, right? And it's going to a green wave that looks like this. So as the green wave, right, is becoming higher in energy, what we see here is we have more waves. More waves per unit of time leads to a higher frequency. Right? It's a higher frequency. Now, notice what happens to the wavelength as you go from a lower energy, right, to a higher energy. You get a higher frequency, but you get a shorter wavelength. So all you have to do for this question was tell me that the second reaction, right, in this situation, the green wave has a higher energy because it has a higher frequency and thus has a shorter wavelength, right? A shorter wavelength. That's all you had to explain, right? Looking at the numbers in the wavelength, you can see on the table to the left that the wavelength is shrinking as you go from red to violet. Smaller wavelength means that you have more waves per given unit of time. More waves equals more energy. Think back of the wave machine that we did in class. That's literally all you had to do for question number 3 was explain that. Now, if you calculated it, that's fine. Okay, but you didn't need to. You could have seen that if you understood energy and waves, frequency, and the relationships, then that would have made sense. Okay. All right. So that's it. That's all you needed to do for the first set of questions. Let's move on to the second set of questions here. So I'm going to draw a little line here. Let's see. Let's do it in black. Okay. Let's draw a little line so we can separate these questions. Okay. With the metal you have identified, draw the structure of the compound the metal would form with the ion phosphate. Okay, so in this case, we said that we saw red, so a fair color would have been lithium. So I'm going to use lithium, okay? Again, for the following questions, use the table to the right, which in this case is the top, to determine the metal that was used in the reaction. So based on the color that we saw, I'm going to go with lithium. If you had green, you could have chosen copper. If it was yellow, it would have been sodium, etc., etc. Okay. So it says draw the ion that would form, or the compound that would form if it bonded to the ion phosphate. So phosphate is PO4 3-. If you had arsenate or arsenite or phosphite, it's the same process. So what I'm going to do first is I'm going to draw this structure. Okay, so I'm going to do my AVBN. Okay, the AVBN is only going to be for phosphate. Okay, I don't need to include the lithium yet. So this is what you need to do to get full credit. Okay, phosphorus has a space for 8, oxygen has a space for 8. I'm going to multiply phosphorus times 1, oxygen times 4. This gives me 8, this gives me 24. If I add them all up, I should end up with 32. 32 spaces. Sorry, that's incorrect. 32 plus 4, that's 40. See? Even I make mistakes. So that's 40 spaces available. Okay? Sorry, I don't know what happened there. Okay, 40 spaces available. Valence electrons. Let's go ahead and do our valence electrons. Valence electrons for phosphorus are going to be 5. Valence electrons for oxygen are going to be 6. There's 1. There's 4. That's probably what I was thinking there. 5, 6 times 4 is 24. That's going to give me a total of 29. But don't forget that this 3 plays a role. That means that somebody somewhere is carrying extra electrons. So we need to add them to the total. That should give us a total of 32 electrons, right? Valence electrons. Okay. But you got to figure out the bonding electrons now. So to take the bonding electrons, I take the value of A, subtract from it the value of V. So 40 minus 32 should give me a total number. 40 minus 32 gives me a total of 8 bonding electrons. Okay, and let's just go ahead and take care of this value now. That's going to be V minus B. Right, valence electrons minus bonding electrons. So I have 32 valence electrons, and 8 of them are bonding, so I should have 24 non-bonding electrons. Okay, so let's go ahead and draw our preliminary structure for phosphate. So that's going to be a P in the middle, surrounded by 4 oxygens, right? Now, if you had phosphite, it would be 3 oxygens, and the same thing would happen with arsenate and arsenite. Okay, I have 8 bonding electrons. If I divide that by 2, that means I should have 4 bonds. So here's my 4 bonds. All right. Once I have my 4 bonds, I go through and I add all of my non-bonding electrons, which should equal a total of 24. And if you do 6 times 4, you end up with 24. So here's my preliminary structure. There it is. Okay. Now, what I got to do now is I got to calculate the formal charge for each one. So let's do phosphorus first, right? The formal charge tells us whether our structure is going to be stable or not, right? So we got to do the formal charge. Formal charge is equal to the number of valence electrons on an element minus the number of bonds on that element minus the number of non-bonded electrons on that element. So if we're going to do phosphorus, let's take a look at phosphorus, which is right here. Phosphorus, we know, going up here, from its V, that it has 5 valence electrons. So there's 5. This phosphorus has 1, 2, 3, 4 bonds on it, so I'm going to subtract 4. And then the phosphorus, in this case, has 0 non-bonded electrons, so this phosphorus has a formal charge of +1. Okay, let's do oxygen now. Oxygen has 6 valence electrons, right? We'll do this one right here. 6 valence electrons, it has 1 bond on it, and it has 6 non-bonding electrons, so it has a formal charge of -1. Now, if you notice, all the oxygens in this structure have exactly the same setup, so we can all say that they have a -1. Now, you can see here that if I take -1, -1, -1, -1 for all the oxygens, right? Here, 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 and here, and then that gets me to -4, but then I add this +1 here, then the overall charge is a 3-, right? That's how you justify the oxidation state in question 1B on the second set of questions. That's what I was asking you to do. Draw the formal charge and give me the overall charge of the structure. In this case, it's a 3-, but we already know that because of this guy right here. The formal charge just tells you why the phosphate carries a 3-. You have 4 oxygens, each with a -1 formal charge, and then you have a phosphorus with a +1 formal charge. Thus, you end up with a 3- overall charge. That's what that means. This, guys, is the oxidation state. Okay, it's just a fancy way of saying charge. Okay, now, what does the formal charge tell us? The formal charge tells us that the structure is not in the most stable form. Remember, we want the center atom to be at 0, so we don't have a back and forth with the electrons, right? So we need to change the structure in a way that we can change the number of bonds, right? And get that formal charge back down to 0. So how do we do it? Okay. All right. So what we're going to do is we're going to just pick any one of these oxygens, right? Any one of these oxygens, and we're going to move the electrons. Let's pick this one. We're going to move the electrons, and we're just going to create a double bond here, right? By creating that double bond there, then I'm going to erase these here, right? And that double bond now changes the formal charge of phosphorus, right? So how does it affect the formal charge? Well, if you recalculate, phosphorus has 5 valence electrons, right? This one now has 5 bonds on it, and it still has 0 non-bonding electrons, so it has a formal charge of 0. So now phosphorus is a 0. This oxygen is also going to change. It has 6 valence electrons. It has 2 bonds on it, right? Because there's 2 there now. Minus 4 non-bonding electrons. It used to have 6, remember? And 6 minus 2 is 4, minus 4 is 0. So now this one changes to a 0. Once again, remember that these guys have not changed. So these guys are still -1. And if you look and you add up all the formal charges, right, then you see that it still carries an overall -1 charge. So the question for the oxidation states of the ion, for the overall oxidation state still holds true, because even though we're changing some of the formal charges, the overall charges are still in the area of -3. Okay, so this is what's represented as our final structure. All right, now resonance structure, remember, is acknowledging that this double bond here can be anywhere on the molecule. It doesn't necessarily have to be at this oxygen. We could have done it here. We could have done it here. We could have done it there, right? So the resonance structures are just another representation acknowledging that that double bond can exist anywhere on the molecule, right? Now, when it comes to resonance, you don't have to draw all of them. Mirror images don't count. So I don't have to draw the one at the top here because that's a mirror image. The only one I have to draw is one on the side. So the other resonance structure for this particular molecule would have been phosphorus with the double bond here, or on the other side, right? Remember, mirror images don't count. And that would have been your resonance structures for this particular molecule. Okay, so there it is. Now, it doesn't matter which one you draw. It doesn't matter. If you drew all 4, you just got even more credit. But resonance structures is just saying that that double bond exists in multiple places. So you have to show that. Okay, Remember, these guys still carry a -1, a -1, a -1, a 0, and a 0 in the center. They still carry a -3 charge. Okay. Now, the original question was asking where the lithium would bond. Well, remember that lithium oxidizes 1 electron to become lithium 1+. Okay. Now, if I'm a positively charged lithium, right, and I'm bonding to phosphate, right, where would I bond? Would I bond to the phosphorus? Would I bond to one of the oxygens, right? Would I just create a whole new compound? So you got to remember, guys, this plays a huge role. Whoops. This plays a huge role. The 1+ right here. If I'm positively charged lithium, I'm going to be attracted to the negatively charged oxygens. And it's going to form an ionic compound. So this compound here is covalent. Okay. When this entire compound bonds to the lithium, then I'm going to bond to where I have an opposite charge, right? So lithium that is now a positively charged ion is going to bond here. It's going to bond here. And it's going to bond up here, right? Why do we need 3 lithiums? Because remember, the charges have to cancel out. If these charges were to add up, I would need 3 lithiums, right, to cancel out the 3- charge from the phosphate and form this chemical formula. Okay, Li3PO4, right, is the reason that it's Li3 is because you need 1, 2, 3 +1 lithiums to cancel out each -1 on the phosphate. If you got to the point where you bonded lithium to phosphate, you got most of your credit, but you needed to have 3 lithiums, right, in order to get this done. So what's the name of this compound? Well, it's an ionic compound now, so it's just called lithium phosphate. That's it. That's all the answers in the... Bells are driving me crazy. It's an ionic compound, and that's all you need to do for the second set of questions, right? This is all for question number 1A, B, and C. It's all here. All right. Keep in mind it's taking a little bit longer because I'm trying to go step by step. If you feel like I'm going a little fast, pause the video, go back, watch it again. Stop me. Okay. Explain how the compound would change if phosphate ion became an acid. Draw the correct structure. Name the acid that would form. Okay, so look, you already have the structure here, guys. You already drew it. Why? You don't have to reinvent the wheel. So look, phosphate. I'm going to draw the double bond up here now. Oh my God. Draw my other oxygens. Okay. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This one only gets 4, remember? Okay. Again, here are your -1s. Here are your -1. Here are your -1. So hydrogen is going to form a +1. If hydrogen was to bond to the phosphate, you would have a hydrogen bonded here, a hydrogen bonded here, and a hydrogen bonded there, right? The only difference between this compound and the other one is that now it's with hydrogen. But it's exactly the same, guys. Now, this is the structure for the acid that would form with the phosphate ion. What kind of acid is this? Well, it's a polyatomic ion. It's more than one atom, and there is oxygen, so this is going to be a oxyacid. So what is this guy called? It's called phosphoric acid, right? If you had arsenate, it'd be arsenic acid. If you had phosphite, it would be phosphorus acid. And if you had arsenite, it would be arsenous acid. Remember, ATE, polyatomic ions, equal the IC ending, and the ITE, polyatomic ions, equal the OUS endings. Okay, so that's all you had to do for this one. You already had the structure. All you had to do was add the oxygen in the place of the metal, and you have an acid. What is the chemical formula? The chemical formula for this one is going to be H3PO4. That's all you needed to do to get full credit on the last question there. Okay, let's look at the phosphate molecule a little bit deeper. Draw the Bohr model structure of the phosphate molecule to show the bonding and explain the difference within the molecule as opposed to when it's bonding to the metal. Okay, so all you had to do here was to draw the Bohr model for phosphorus. In this case, phosphorus is in the third energy level. So 1, 2, 3, 1, 2, 1, 2, 3, 4, 7, 8, and then 1, 2, 3, 4, 5. Okay. All right. Now, phosphate in this case is being bonded to oxygen. So oxygen is going to be here. All right. Here, I'm kind of drawing these really bad. Here. And here. Okay. What you needed to show me was just that these electrons are being bonded. Show me the double bonds, show me the single bonds, and that was it. That was all you had to do for the Bohr model, right? Now, what's the difference? Well, within the molecule of phosphate, we have a covalent bond. We have a covalent bond. That means here, electrons are being shared. They're being shared to achieve octet or a full shell, right? When the phosphorus bonds to the lithium, right, here, now this becomes ionic, right? One, because it's a metal, right? And the other one, because we said earlier, remember, that phosphate has a 3- charge because somebody's carrying extra electrons. Well, those extra electrons are on all the oxygens that have the -1. So the idea is if you're bonding to lithium, lithium is the one that gives the extra electron to the oxygen here. See it? Lithium here. Should have drawn this better. And lithium here, right? So the oxygen has a full shell, right? Because the lithium gave its extra electron to each one of these oxygens, and then this oxygen became negatively charged. Lithium, as a result of oxidizing and giving up its electron, became positively charged, and then they became electrostatically attracted to one another, right? And they create a bond. So that's all you had to explain, right? The electrons are being shared within the phosphate molecule, creating a covalent molecule. The lithium donates electrons to the oxygen, or you didn't even have to go that detail. Just say lithium oxidizes, and as a result of having a positive charge, is now being attracted electrostatically to those negatively charged electrons and becomes an ionic bond. Okay? All right. So here's the exam in a nutshell. If you look at it, there really wasn't anything here that should have been overly difficult for you to do in our group. Go ahead and upload a picture of your notes, and that's it, guys.